Hello everyone, I'm Mark here with Studyclix, and in today's video we're going to be having a look at the Higher Level of Physics 2020 paper. We're going to be looking at question 5, which is the multiple choice question. It's a question that comes up every year, and personally I think it's my favourite question on the exam because it's a great place to start. It's a great place to settle your nerves, and in this question you get a lot of choice, which is just a great way to start in my opinion. We're asked here to answer 8 of the following parts. Each question gets 7 marks, so there's a total of 56 marks going in this section. But I will recommend to you now that you do more than the 8 you're asked for, because it's always nice to have, different topics that you can pick and choose from, but it's a great place to pick up marks, and doing more than 8 means if you get one wrong or make a small mistake, it means you still have a shot at getting the full 56 marks. So let's get straight into part A. Part A is a straightforward definition question. It asks us to state Boyle's law, and it goes as follows. The volume of a fixed mass of gas measured at constant temperature is inversely proportional to its pressure. For this question, there was a total of 7 marks going. You got 3 marks if you mentioned that there was a fixed mass of gas. You got another 2 marks for mentioning that it was measured at a constant temperature. And you got your final 2 marks saying that the volume is inversely proportional to the pressure. In part B, we are asked a question on density. We are told that there is a neutron star that has a density of 3.7 by 10 to the 17 kilograms per meter cubed. And we are asked what would the radius of the Earth be if it had the same density as the neutron star. Another piece of information given to us in the question is the mass of the Earth. In this case, it's given as 6 by 10 to the 24 kilograms. Whenever I see a question like this, alarm bells go off in my head when I see the word density. I'm now going to go to my log tables and look for the formula that uses density. By going to page 57 of our log tables, we find the formula for density. The formula for density is given as rho, our density, is equal to our mass divided by our volume. We are now going to use this formula in the question above. In the question above, we are told the density of our neutron star. We are now going to use the formula that we found below to find the volume of the Earth if it had the same density. The reason we are doing this is that we can then use the formula for the volume of a sphere to find the radius of the Earth if it had the same density. Here is the formula we found in our log tables. Rho is equal to mass over volume. We are now going to sub in the information that we know. The density in this case is 3.7 by 10 to the 17 kilograms, and we are then going to plug in our mass of the Earth. When we plug in the information given to us in the question, we get the following formula. 3.7 by 10 to the 17 kilograms per meter cubed, our density, is equal to the mass of the Earth, 6 by 10 to the 24 kilograms, divided by the volume. We are now going to rearrange to find the volume. Now we're going to plug in the information that we have in our formula into our calculator. On the top of our fraction, we're going to have 6 by 10 to the 24. This is our mass of the Earth in kilograms. On the bottom, we're going to have our density, 3.7 by 10 to the 17 kilograms per meter cubed. Pressing equals here, we get a number for the volume of the Earth if it had the same density as the neutron star. We are now going to write this using scientific notation to make it simpler to read. Here we get the volume of the Earth to be 1.62 by 10 to the 7 meters cubed if it has the same density as the neutron star. If we go back to the question though, we notice that we are asked for the radius and not for the volume of the Earth. What we now need to do is convert this volume into a radius. Like I said before, we're going to use the formula to find the volume of a sphere. The reason we're going to use that is because in that formula we use the radius. The formula to find the volume of a sphere is given as 4 over 3 pi r cubed. And we are now going to sub in all information that we have from before. We are going to let this formula equal to the volume that we found earlier. 1.62 by 10 to the 7, and this is going to equal to 4 over 3 pi r cubed. We are now going to rearrange to find r on its own. Rearranging to find r, we find the following equation. If we take the cubed root of 3 times the volume divided by 4 pi, we'll be able to find the radius of the Earth. Now we're going to plug this into our calculator. To get the cubed root function on our calculator, we're going to press shift and we're going to press this button here. Inside this, we're going to have our fraction, and we're going to have 3 times 1.62 by 10 to the 7, our volume that we found earlier, divided by 4 pi. Pressing equals here, we'll get an answer for our radius. Here on the calculator, we see that the radius is equal to 156.967 meters. Rounding to the nearest meter, we're going to find the radius to be 157 meters. Here I've written out that our radius is going to equal to 157 meters when rounded to the nearest meter. Much like every question in this section, there are 7 marks going. You got 3 marks if you use the formula to find the density and subsequently find the volume. You got another 2 marks if you mentioned that the volume is going to equal to 4 over 3 pi r cubed for a generic sphere. And finally, you got a final 2 marks for getting the answer rounded to the nearest meter. In this case, it's going to be 157. In part C, we are asked to calculate the natural length of a spring given the information in the question. Here we are told that the length of the string is 22 centimeters when a 2 Newton weight hangs from it. And finally, we are told that the spring constant is 50 Newton meters. We're going to use this information now to calculate the natural length of the string. Much like every question, if I don't know where to start, I normally look for the language in the question and try to find a formula using the information given. Here we are told that there is a spring constant and that it is 50 Newton meters. If you recall from the chapter on mechanics, spring's constant is used in Hooke's law. I'm now going to go to the log tables to find Hooke's law. By going to page 57 of our log tables, we find the formula for Hooke's law. In this case, it's going to be F, our restoring force, is going to equal to minus Ks. K here being our spring constant and S being our displacement. Going back to our question, I am now going to use the information given and we're going to put it into our formula. The formula we found earlier is that F is going to equal to minus Ks. In the question, we are told that a 2 Newton weight hangs from the spring. In this case, the 2 Newton weight is going to be our force, and I'm going to write it down here for F. I'm going to let this equal to minus K. K in this case is our spring constant, which is 50 newtons per meter. And finally, we have S. We are now going to solve for S, which is going to be our displacement. By dividing both sides by minus 50, we'll be able to find our answer for S. Writing that out fully, we see that S is equal to 2 divided by minus 50, which is going to equal to 0.04 meters. The reason that this is measured in meters is because the meter is the SI unit for displacement. Now that we have found our displacement though, we must go back to our question, because in our question we are not asked for the displacement, but instead we are asked for the natural length of the spring. The natural length of the spring is going to be the difference in our length and our displacement. In this case, if we take 0.04 meters away from 22 centimeters, we'll be able to find our answer. Before we continue though, we must convert our length of 22 centimeters into meters. In this case, 22 centimeters is the same as 0.22 meters, and from this we're going to subtract 0.04 meters as well. If we put this into our calculator, we will find the answer to be 0.18 meters. This is the same as 18 centimeters, and this is our final answer for the natural length of our spring. In this question, there were 7 marks going, and you got 3 marks for identifying the formula for Hooke's law. You got another 2 marks for mentioning the displacement S, which we found here, and you got a final 2 marks for finding the correct natural length of the spring, which is 18 centimeters or 0.18 meters. In part D, we are asked to draw the image formation in a convex mirror. The important part of this question is identifying what a convex mirror actually is. Now, this is one of the important things on the optics section of the physics course, and there's only 2 types of mirror really covered in it. There is a convex mirror and a concave mirror. The way I remember the difference is a concave mirror caves in, so in this case a concave mirror is this one on the left, and a convex mirror is just the opposite. So if one caves in, then the convex mirror is going to bow out like this, and this is known as a convex mirror. As we see down below, I have drawn our convex mirror here. And what we're going to have is the convex mirror is going to be sitting on something known as the principal axis, which is this line down here. On the left hand side, we've drawn a large arrow here, which I've called A. This is going to be our object, and I've just called it A just for simplicity. And A is sitting at the point B along our principal axis. A few things to know here is that halfway along our principal axis or so, we have our convex mirror. And behind our convex mirror, we have the points F and C. F and C in this case stand for our focal point and our centre of curvature. Now, as rays come from our point A, or object A, if they're going parallel to the principal axis, they're going to rebound as if they originated from the focal point. As we can see here, rays coming from A are going to travel along parallel to our principal axis, hit the point along the convex mirror, and rebound as if they came from the focal point behind the mirror. This line here behind the mirror, joining the convex mirror to the focal point, is represented by these dotted lines. And similarly, if we repeat the process for a ray coming from the object A but going towards the centre of curvature, we get another such line. In this case, rays coming from A going towards the centre of curvature will hit the convex mirror and entirely rebound along the path they travelled. For example, if we have the ray coming like this, once it hits this point, it's going to bounce back and it's going to be coming that way. Now, similar to before, I've shown that the line behind the convex mirror, and I've represented using dotted lines going from our convex mirror to the centre of curvature point C, which is over here. Now, as you can see, these two lines are going to intersect at a point A, and this is behind the mirror, so we're going to get a virtual image, which we're calling A prime, which is our virtual image of A. And this is going to be at a point B, which is behind the mirror, which we're going to call B prime. As well as this, I've also marked in a few other pieces of information: our object distance, the distance from B to the convex mirror, and our image distance, which is going to be the distance from the convex mirror to the virtual image, which is behind the mirror, which is known as B prime in this diagram. Now, similar to before, there was 7 total marks going for this question. You got 3 marks for drawing the object and the correct mirror. So in this case, A here and the convex mirror, the correct one, as we said before, concave and convex, making sure you know which one's which. You got 3 marks. You got 2 marks for drawing correctly the rays coming out of the object A and striking the convex mirror. So on the left hand side here we have the 2 rays which I've annotated in purple. And you got another 2 marks for correctly drawing the dotted lines behind the mirror and also the correct image and its position, which in this case is going to be A prime, which we'll show over here. Another thing to note is, just for the clarity of when you're doing this yourself in the exam, using dotted lines behind the mirror makes it easier for the examiner to understand the difference between the real ray and the virtual ray. And yeah, for this question, that's how the marks were best split up. In part E, we are asked, what is meant by the amplitude of a wave? Below here, I've drawn a small diagram to help understand what the amplitude of a wave is. On the right hand side, I have given the actual definition, which is what the question is asking for. But first, let's go through the small diagram. In the diagram on the left, we have an x-axis and a y-axis. In this case, our x-axis is going to be labelled as our rest position. This is the average position of the wave. As the wave moves up and down, here we see that at different points it will be the furthest from this rest position. Here I've labelled these points are amplitudes. An amplitude can go up or it can go down. In the definition given on the right, the amplitude of a wave is the maximum distance of the wave from the wave's rest position. In the diagram here on the left, we can see the amplitude is when the wave is furthest from our x-axis or our rest position. This question also had 7 marks going. You got 4 marks if you mentioned the fact that this was the maximum distance, and you got another 3 marks for mentioning that it was the displacement from the wave's rest position. In part F, we are asked to name one of the 3 primary colours of light. In the second part, we are asked to name its complementary colour. Complementary colour is defined as a colour that is combined with another that makes white. And our 3 primary colours are red, green and blue. So our complementary colour is any colour that mixes with either red, green or blue to give us white. On the left hand side, I've drawn a little diagram showing how these colours mix and match to give us our different combinations. The bigger circles on the outside are our primary colours. We have blue on the bottom left, green in the top middle and red on the bottom right. When blue and green mix, we get our cyan. When green and red mix, we get yellow. And when blue and red mix, we get magenta. If you follow the diagram, the intersection of the 2 primary colours across from any given primary colour will give us white. For example, if we look at green, the intersection of the 2 across from it will give us white. In this case, it's magenta. If we look at purple, the intersection from the 2 primary colours on the other side, green and red, in this case giving us yellow, will give us our white. This means that if we mix yellow and blue, we will get white. This is personally how I find it the best way to remember this system. It means that you can give lots of different combinations if you can't remember one off the top of your head. But down below, I've written our colour combinations. On the left, I've written our 3 primary colours, green, red and blue. And on the right, I have said the complementary colour that when mixed with our primary colour will give us white. In this case, the complementary colour, magenta, cyan and yellow respectively. If you give any combination of these, you will get full marks in your question. This question is also worth 7 marks. You get 4 marks for giving our primary colours. In this question, any one of the 3 will do. And you get your final 3 marks for giving any one of our 3 complementary colours, as long as it is paired with its respective primary colour. I.e., you can't say green and cyan because green's complementary colour is not cyan. Red's complementary colour is cyan. This is worth 3 marks, giving us our total of 7. In part G, we are asked to draw a label diagram to show an electric field pattern and how it can be demonstrated in the lab. Unfortunately, this is just a diagram that you have to learn off, but below I have the required diagram. Here we see a plate with a thin level of oil sitting across it. Sprinkled on top of this oil is semolina powder. As well as this, on top of the plate are two smaller plates with a voltage source connected across them. When the voltage source is switched on, a voltage or potential difference will exist across the two plates inside the oil. This will cause the semolina powder to rearrange itself into the shape of the electric field lines passing through the oil. The powder arranges itself in the shape of the electric field passing between the two electric plates, and this is how we see the line. And this is how electric field patterns can be demonstrated in the lab. 3 marks were going if you mentioned the oil and the semolina powder. As well as this, 4 marks were going if you mentioned the plates and the voltage source connected across them. Part H asks us to distinguish between intrinsic and extrinsic conduction in a semiconductor. These are two standard definitions and they go as follows. Intrinsic conductors are pure conductors with an equal number of holes and electrons present, while extrinsic conductors are impure conductors that have undergone some kind of doping. In this case, doping means the controlled addition of impurities. That means the conductor has more holes or more electrons present. 4 marks were going if you mentioned how pure the conductor was. In the case of intrinsic conductors, it means saying that the conductor was pure, and in extrinsic conductors, it means saying that they are impure. To get the rest of your marks, you had to mention the number of holes and electrons present. In intrinsic conductors, an equal number of holes and electrons are present, while in extrinsic conductors, this number can vary. In different conductors and different materials, we can have extra holes or extra electrons. In part I, we are told that the diagram here shows a sketch of a photocell. We are then asked what particles move between the electrodes within the photocell and in what direction do these particles move. The answer to the first part of this question is that the particles that move between the electrodes inside a photocell are electrons. The second part of the question asks us about the direction of these particles. The answer to this is that the electrons move from the cathode to the anode. Just like every other question in this section, there were 7 marks going. You got 4 marks for saying that the particles moving within the photocell were electrons. And you got 3 marks for saying that the electrons move from the cathode to the anode inside the photocell. This gives us our total of 7 marks. In part J here, we're given 2 different questions that we can do, part A and part B. And as with all of these multiple choice questions, part J allows us to pick between 2 different ones because normally the first one is a question on nuclear physics and particle physics, while part B tends to be a question on applied electricity. And the reason for this is because some teachers choose to do the applied electricity part of the course and some choose to do the particle physics, so obviously you get a choice to do one or the other here. Now, if you've done both, yet again, obviously a great opportunity to do both here. No problem doing both as well. But for part A, we'll just have a look at part A first. So in part A, we're asked to write a nuclear equation to show pair annihilation of a positron and an electron. The important parts of this to note is we were asked about pair annihilation and we're asked about a positron and an electron. In the diagram below, I've given a sense of what this would look like. And the reason I've drawn a diagram here is personally I always find it best because it helps me visualize what's going on and helps me kind of break down the question into pieces. The diagram here on the left shows our electron and our positron. I've just drawn these as little circles, but you can write positive and negative in them just to kind of help you understand what's going on. And when these two collide with each other, they go through something called pair annihilation. And what happens is 2 gamma rays are emitted once they have collided. Now we're asked here to draw a nuclear equation for this, so the diagram isn't enough. And to do that, we're going to draw out our nuclear equation. So on the left-hand side, we have an electron and we have a positron. So the way we'll denote an electron here is an electron is going to be E with a minus charge, and a positron is going to be the same as an electron, but just the opposite charge. So it's going to be E with a +1 charge. And when they collide with each other, they're going to transfer or change, and we're going to denote that by this little arrow here. And as I said earlier, once these two collide, they're going to give rise to 2 gamma rays, which I'm going to represent here as 2. Now, gamma, this letter here, if you haven't seen it before, is just the symbol gamma. It's just how you represent 2 gamma rays. Another way you can represent this here is by using the symbol HF, which is just the normal way for denoting the energy in a wave. Now, as always, this question is worth 7 marks, and because A and B are, you can choose one or the other, they're both worth 7 marks individually. And in the case of this one, you got 2 marks for correctly writing down the symbol for an electron. So over here we're going to have 2. We're going to have 2 more marks for writing down correctly the symbol for a positron. And finally, you got your last 3 marks were split up into a 2 and a 1. You got 2 marks for correctly showing that there was 2 gamma rays, or 2 gamma rays emitted, and you got 1 mark for correctly showing the way to write down this ray. So if you use the Greek symbol gamma, you got a mark, and you also got a mark if you used HF, and because they're interchangeable, it doesn't matter which one you used. And that's the breakdown of the marks in this question. So the way to tackle questions like this, I always find easiest is to draw a wee diagram, especially for particle physics, draw a wee diagram and kind of use it to reason out this nuclear equation. And the reason that this works is because we have something known as the conservation of charge and the conservation of momentum. And on the left-hand side, if you look, we have an electron and a positron with a charge of -1 and a charge of +1, respectively. And if we add them together, that means on the charge on the left, we're going to have a net charge of 0. And on the right-hand side, we have 2 gamma rays, or 2 photons, should I say. And in this case, the charge on a photon is 0. So on the right-hand side, we're going to have a charge of 0. And that means that there is no, the conservation of charge is present here. 0 goes to 0. There's nothing changing there. And the reason that we can explain the way that they move off at different angles to each other is shown by our momentum, or should I say our conservation of momentum across the reaction. But yeah, this is how we break down the 7 marks for the nuclear equation. In this question, in part B, you also have the option to do the question on applied electricity. The question in this case asks us to draw the truth table for an OR gate. In part B, I have drawn the diagram here for an OR gate, and on the right hand side I have drawn our truth table. An OR gate has 2 inputs, in this case labelled A and B, and it has 1 output, which we have labelled here Q. Our truth table goes as follows. When both A and B are 0, our output is also 0. When A is 1 and B is 0, our output is 1. When A is 0 and B is 1, our output is also 1. And finally, when A and B are both 1, our output is 1. In short, when either of our inputs A or B are 1, we get our output of 1. This means that if A or B are 1, or even A and B are both 1, we get our output as 1 as well. This question is also worth 7 marks. You got 2 marks for your first line, 2 marks for your second line, 2 marks for your third line, and finally 1 mark for your last line.